Hello, welcome to today's class. In today's class, we will talk about binary logic. So, binary logic consists of binary variables and logic operations. So, by binary variables, we mean variables which can take one of the two possible values, 0 or 1. And there are three basic logical operations: AND, OR, and NOT. We already know what are truth tables. So a table of all possible combinations of the variables showing the relation between the values and the variables may take and the result of the operation. Let us look at the truth table which can actually define the three logical operators. So here is the truth table for the logical AND. In this truth table we can see that we have two variables x and y, and since we have two variables we can have four possible combinations of the input variable values which is 0 0 0 1 1 0 and 1 1. And the next column here, it shows the value of x and y. So here we are using the operator dot to signify the logical AND operation. So please note that this dot is not the multiplication, but it actually signifies the logical AND operation. And now from the truth table we can see that whenever any of the variable is 0, the output x and y will result in 0. For example, x0 and y0, x and y will be 0. If x is 0, y is 1, x and y will be 0. If x is 1, y is 0, then also x and y will be 0. X and y will be 1 only when both the input variables are 1. So this is how logical AND is defined. Next is the truth table for logical OR, and here we can see that the notation for the logical OR operation is plus. So this plus do not mean binary addition, it does not mean addition, it means the logical OR operation. And from the truth table we can see that only when x is 0 and y is 0, that x or y will be 0. Otherwise, if any of the variable is 1 or both the variable is 1, x or y will be 1. So for 0, x equal to 0, y equal to 0, x or y will be 0. For x equal to 0, y equal to 1, x or y will be 1. X equal to 1, y equal to 0, then also x or y will be 1. And finally when x is 1, y is 1, then also x or y will be 1. And so this is how logical OR is defined. And finally the logical NOT operation, it's a unary operation, and here we have the variable x. So now we have only two possible rows. X can be either 0 or it can be 1, and here is the output. And if you see the logical NOT operator is represented by the prime symbol. So we have x and then we have x prime. And from this truth table we can see that when x is 0, x prime NOT of x will be 1, and when x is 1, NOT of x will be 0. So this is how the three basic logical operations are defined. And now logical operations could be carried out by electrical switching circuits. So let us try to understand what we mean by this. For that we will take the example of a switch. Here we have a switch, and the switch can be in either off, or it can be on. So we say that the switch is open or the switch is closed. So the switch can be in any one of the two possible states, and we will use this binary variable x to represent the state of the switch. So when the switch is open, we say that x is equal to 0, and x equal to 1 signify that the switch is closed or it is on. And here is the symbol of the switch that we will use. So this is the symbol of the switch, and now we can have circuit here, and it's a circuit where we are controlling a light using the switch. So here the switch is connected to the battery, and when the switch is on or when the switch is closed, this path will be closed, and hence there will be flow of current and the light will be on. And if the switch is open, that means the switch is off, then this path will be broken and the path will not be closed, and hence there will be no flow of current, and hence the light will be off. It's the same diagram shown here, only that instead of a battery, we are connecting this to the ground, so the return path is through the ground. Otherwise it's the same circuit where we are controlling the light using the switch. Now let us and one more thing, this light can be again in one of two possible state. It can either be on or it can be off, and we will use the binary variable L to denote the state of the light, and we will say that L equal to 0 signify that the light is off, and L equal to 1 signify that the light is on. Now we can try to come up with the truth table which will show the relation between this variable x and the output variable L, and we can try to fill up this table by noting that when the switch is on, that means the switch is closed, which means x is 1. For this condition, your light will be on because the switch is on, hence the light will be on, and hence we can say that when x is 1, the output L will also be 1, because we already said that L equal to 1 signify that the light is on, and since the light is 1, we can say that L is 1. Now the other case is when the switch is off. If the switch is off, there will be no flow of current, and hence the light will also be off. And the fact that the switch is off is signified by the value x equal to 0, and when x is equal to 0, the light is off, which means L is also equal to 0. So this is the truth table for this circuit, and from this truth table we can come up with this logic expression that L is equal to x, because it is evident from this truth table that when x is 0, L is 0, and when x is 1, L is 1. So whatever is the value of x, that would be the value of the output variable, and hence we can say that L is equal to x, and this is called a logic expression. And this logic expression here is describing the output L as a function of the input x, and it's also called a logic function where x is the input variable. So L is a logic function of the variable x, and the function is defined as L of x is equal to x. Now let us look at another circuit where we have two switch, and the state of the first switch is denoted by the binary variable x1, and state of the second switch is denoted by the binary variable x2, and we have connected the two switch in series. And now if we again try to come up with the truth table for this circuit, we will see that when both the switch are off, the path will be broken, hence there will be no flow of current, and hence the light will be off. Now the fact that both the switch are open is signified by x1 equal to 0 and x2 equal to 0. And when both are off, the light is off, so we can say that L is equal to 0. Now if we turn the switch x2 on, this will be the situation. Switch x2 is on, but switch x1 is off, and since this switch is off, this path will be broken here, and hence there will be no flow of current. And this situation where x1 is off will be represented by x1 equal to 0, s2 is on, which will be represented by x2 equal to 1, and in this case the light is off, so L will be equal to 0. Now if we turn on switch x1 but turn off switch x2, then also this path is broken at this switch, and hence there will be no flow of current, and again the light will be off, and thus we can say that when x1 is 1 and x2 is 0, light L will be 0, it will be off. And finally, when both the switch are on, we now have a closed path, and hence there will be flow of current, and hence the light will glow. So we can say that when x1 is 1 and x2 is 2, our L will be equal to 1. And now if we look at this truth table closely, we will see that this is nothing but our logical AND operation. And hence we can say that our output L, which is now a function of two variables x1 and x2, is defined by x1 and x2. Continuing our discussion, let us look at the next circuit, and here we again have two switch, but this time the two switch are in parallel, they're not in series. In the earlier case the two switch were in series, but now we have the two switch in parallel. And for this circuit, let us try to build the truth table. And if we have both the switch off, then this path is also broken and this path is also broken. Both the path are broken, and hence there will be no flow of current, and hence this light will be off. And this we can represent it as when x1 is 0, x2 is 0, L will be 0. But if we turn on the switch x2 and our switch x1 is off, now we have a path which is closed. This path is broken. The path through switch x1 is broken, but the path through switch x2 is closed, and hence there will be flow of current here and the light will be on. Thus we can say that when x1 is 0 and x2 is 1, output L will be equal to 1. Now instead, if we have x1 on and x2 off, still we will have a closed path. This path through x1 is closed, and hence there will be flow of current, and hence this light will be glowing. And this we can represent it we can represent as when x1 is 1 and x2 is 0, L will be equal to 1. And finally, when both the switch are closed, that means both the switch are on, then both the path are closed, and hence we will again have flow of current here and the light will be on. Thus we can say that when x1 is 1, x2 is 1, L will be equal to 1. And again, if we look at this truth table closely, this is nothing but our logical OR operation. And hence we can write the logic expression as L, which is a function of x1 and x2, is defined by x1 logical OR x2. And let us look at the next circuit here. Here the switch and the light is connected in parallel. And let us now try to build the truth table for it. Now when the switch is off, this path is broken. However, we have a closed path here, and hence there will be flow of current and the light will be on. So when x is 0, the switch is off, so x is 0, our light will be glowing, so L will be equal to 1. Now if we turn on the switch, then this path will short circuit the light, and hence there will be no flow of current through this path, whereas there will be flow of current here. Since there is no flow of current here, the light will be off. And hence we can say that when x is 1, L is equal to 0. And now this truth table is nothing but our logical NOT. And hence we can write our logic function as L of x1 is equal to x1 prime. So this variable is x1. So thus we can see that logic operations could be carried out by electrical switching circuits. We have seen 3 different electrical switching circuits, and we saw they implement the logic operation AND, the logic operation OR, and the logic operation NOT. And this uses of electrical switches to implement logic is the fundamental concept that underlies all electronic digital computers. Of course, in case of the digital computers, the switches will be implemented by transistors. So we have transistors which will act as a switch, and by virtue of being a switch, they will be able to implement logic operations as we have seen in the earlier examples. This fact that logic operations could be carried out by electrical switching circuits was first determined by Charles Sanders Peirce. This would be Peirce in 1886. His work was further expanded by Akira Nakashima, and he discovered a two-valued Boolean algebra which can be used to describe the operation of switching circuits. Boolean algebra we will look at in the next class. And further, Claude Shannon he further elaborated on the use of Boolean algebra in the analysis and design of switching circuits. And actually Shannon's master's thesis became the foundation of the design of modern digital circuits. So his work, which he performed in 1937, is considered as a very significant work in this field of digital circuits. So with that, we will end today's class. We will meet again in the next class. Bye.